Hi, my name is Josue.
Hi, I'm Caesar.
I'm Jacqueline.
My name is Matthew.
I'm Marin.
I'm Diego.
I'm Delaney Babcock.
I'm Fausto Catani.
I'm Tristan.
I'm Gabriel.
I'm Melissa.
I'm Aaron.
I'm Allison Richter.
I'm Mark.
I'm Priscilla Alvarez.
My name's Esteban.
I'm Melissa.
I'm Daniel.
And we're the Cal Poly Pomona Steel Bridge team. Our team prioritizes 3 goals throughout the design process. 1, to achieve a maximum vertical deflection of 1 inch and a maximum lateral deflection of 0.5 inches. 2, to accomplish a 3 to 4 minute build time. And 3, to produce a budget between $2 to $3 million. A good design makes use of materials efficiently. It considers the ease of construction and fabrication and allows for the bridge to function properly under expected loads. Our design process begins with the use of modeling software such as Civil 3D, AutoCAD, and SAP 2000. Sections of the bridge are first drafted in Civil 3D and later structurally analyzed using SAP 2000 under various load case scenarios. The decking is first to be designed, consisting of 20-foot continuous stringers for the base. Simple columns are made up of singular 1-inch tubings and implemented in order to control the sway of the bridge. Next, the arch is designed coinciding with the webbing and the end cross braces to allow for continuity between the pieces. The bridge is ultimately given a sturdier appearance by making the arches thicker than the decking. The seamlessness of the bridge is brought together by the well-aligned members complemented by continuous decking and cross braces. Clean transitions created in part by aspects such as coherent welding, added connections, and hidden pins result in a simple yet elegant design. Point symmetry and simplicity attribute to an aesthetic appeal, in addition to providing strength to the design. During competition, a symmetrical bridge has an unbiased result regardless of orientation during the lateral loading test. The bridge is broken down into individual members to meet the template box requirements. These members are all connected using sleeve, pin, and coin connections. The use of sleeve connections ensure precision and performance under compression, serving as the most convenient option for assembling large pieces. Pin connections are used sparingly in an effort to ensure a quicker construction process and that every member is kept in place to satisfy the template. Moment-resisting coin connections can handle both shear and axial loading and essentially aid in a more efficient process. The bridge is designed in such a way that would allow for an ease in fabrication and construction processes. For example, the deckings were designed in a continuous flat plane. This way, all pieces can be laid flat on a table to be easily sized and welded in place.
Following design, the bridge is then tested under various load case scenarios using CSI SAP 2000 version 16. The software aids in the analysis of the bridge's response to the various prescribed load cases. Results are recorded for estimated lateral deflection, vertical deflection, weight, overall structural deformation, and failure load. The bridge is modeled with design sections, geometries, and connections. Additionally, a 360-degree moment support was assigned at all ground contact points. The variable load cases are separately modeled and analyzed both linearly and non-linearly to ensure the most effective performance during each load case. To further ensure adequate performance, a sizing technique was implemented involving the alterations of cross-sectional areas for each individual member to reduce overall weight and deflections. This is achieved by increasing and or decreasing the tubing diameter and thickness. After the appropriate changes are made to the design, an estimate of the structural bridge cost is calculated. The maximum amount of lateral deflection was 0.32 inches at the point of lateral loading on the south and north side of the bridge, which results in a safety factor of 2. The greatest vertical deflection occurs with the third load case scenario, leading to a result of 0.52 inches, which equates to a safety factor of 1.5. The values remain within the acceptable measurements, even with the added 15% for fabrication error. To test stability, various vertical loads were placed on multiple points along the bridge to measure the lateral deflection. Each load scenario was analyzed to ensure the bridge does not sway over 1 inch under loading. The ground condition, fabrication errors, and construction of the bridge were all taken into account while loading the model bridge in SAP 2000. Hand calculations were performed to verify the results provided by the software.
During construction, a total of 4 builders are used, where 3 are located on the right end and 1 on the left end of the construction site. Having 5 builders was considered. However, the total time conserved from constructing with 4 builders did not outweigh the cost of adding another builder. The third person on the right side will act as a runner for the person on the left side for most of the build, while simultaneously working with the other 2 builders to build the majority of the bridge. To emphasize, a critical pathway and a construction schedule were created to determine the most efficient building sequence. During the construction sequence, builders begin by placing the columns on the footings where the decking would then be assembled. The builders would then proceed with the cross braces, then the arches, and finish off with the webbings. Once finished with the bridge, all builders will use their drill and wrenches to tighten all the nuts to the bolts around the bridge. Lastly, all builders will run to the staging yard and the build will be finished at 3 minutes and 30 seconds.
Our evaluation of the construction sequence efficiency is recorded according to the types of connections that are used. The use of coin connections reduces the amount of loose bolts and nuts, and no power tools are needed to connect 2 members, which allows for a faster construction time. Pre-manufactured sleeve connections are used to connect the arches of the bridge because of the ease and quickness of assembly. Shear bolts are used to allow a faster build because it eliminates the process of having a non-structural part to carry load between 2 pieces. The productivity of the construction build depends on various innovative methods. To begin with, color coding the ends of the pieces with electrical tape will lower the construction time. Color coding the bridge eliminates confusion by indicating the orientation of each piece, which improves the productivity of the build. Another method to increase efficiency is adding a weight to hold up the columns so that they may stand on their own. This allows the builders to construct without holding columns, increasing the efficiency of the build.
With an average deflection of 0.3485 inches and a weight of 183.55 pounds, the overall price, including construction costs, is $2,126,175. Constructability and fabrication are key considerations in the modification of any component. A focus on the efficient cohesion of design compliance, performance, constructability, ease of fabrication, and aesthetics are all part of the designing a bridge with an outstanding final end product.